Welcome to episode 4 of the Ultrasonic Sensing video training series. This video will discuss the difference between the transformer driver and direct driver modes for bursting a transducer. The block diagram of an ultrasonic sensor system can be simplified down to two primary blocks, the driver and receiver. The driver block includes an H-bridge direct driver or a transformer driver to excite the transducer at a single frequency by a digital pulse generator. The objective of the driver block is to maximize the driver voltage across the transducer to generate the maximum amount of transmissible sound pressure. Selecting the appropriate driver is important for two reasons: generating sufficient sound pressure, but also minimizing the ring decay time. The difference between the direct and transformer drivers is solution size, cost, and performance, such that the transformer driver offers superior performance, while the direct driver offers lower cost and smaller solution size. In a transformer driver, the IC provides burst generation by exciting the primary side of a push-pull or single-ended transformer. A DC voltage can be tied to the center tap or high side of the transformer. The objective of the transformer driver is to convert a small DC voltage to a large sinusoidal voltage at the transducer. Many transducers require a driver voltage of up to several hundreds volts peak to peak to maximize the amount of sound pressure generated. The transformer driver stage in the device is realized as two low-side N-channel power FETs. The current limit control of the driver tries to drive current efficiently into the primary side of the transformer to achieve the maximum swing on the secondary side. The secondary side's total resistance, turn ratio, and required peak-to-peak voltage can be used to determine the optimal current limit setting. The current limit block supports multiple current levels, which is set by a register for a typical range of 50 to 500 milliamps. The voltage on the center tap is typically set between 5 to 20 volts. For a center tap transformer configuration, the IC will drive the low side FETs in an out-of-phase manner. The IC can also support a single primary coil transformer configuration where the FETs are driven in phase. For a center tap transformer, the voltage swing on the open drain pins can be as high as 2 times the center tap voltage. If the center tap of the transformer is connected directly to the main power supply that is also shared by the device, then you must take additional precautions to ensure the maximum voltage on the open drain pins does not go above the absolute maximum limits. In a direct driver, the IC provides burst generation by exciting the transducer directly with pulses. Here we show the internal structure for driving an ultrasonic transducer connected directly to the device output using an H-bridge output stage. This configuration makes the excitation supply voltage the peak-to-peak voltage across the transducer in both polarity directions, such that the output driver pulses two half-bridges out of phase. It is also possible to use the driver in half-bridge mode, and is useful for transducers where one side of the piezoelectric membrane must be permanently grounded. The direct driver can also be configured as a pre-driver to drive external FETs or BJTs for higher current and voltage into the primary side of the transformer. The output stage of the device is used as an external low-side driver, similarly to a gate driver. The voltage driver level can be configured to ensure that the out A and out B voltages do not violate the VGS or VBE specifications for the external FET or BJT respectively. In the configuration shown, it is possible to use an external voltage, V boost, which is higher than a supply voltage of the device for generating a larger voltage across the transducer. Deciding which driver mode to pair with your transducer is dependent on your system requirements and the transducer specification. Depending on the transducer model, the excitation voltage requirement can range from a few volts to several hundred volts to generate sufficient sound pressure level. For applications using open-phase transducers, the direct driver is more common because the maximum driver requirement tends to be upwards of tens of volts peak to peak. For applications using closed-phase transducers, the transformer driver type is more common because the average driver requirement tends to be at least 100 volts peak to peak. Although closed-phase transducers can use an H-bridge driver, the maximum detectable range will be less compared to that of a transformer driver due to the low amount of sound pressure generated in the direct driver mode. Comparing transformer drive and direct drive per line item. In performance, the transformer driver is recommended because it can generate a larger transducer excitation voltage when required and allows for the use of additional external matching components to further reduce the blind zone by critically damping the ring decay energy. This means the transformer driver enables the best case minimum and maximum ranging performance. Matching components will be discussed in the next video. In PCB size and cost, the direct driver is recommended because the low driver current requirement allows for the use of a smaller charge capacitor. For example, a transformer driver typically requires a charge capacitor of 100 microfarads, while the direct driver typically requires a charge capacitor of 1 microfarad. The charge capacitor is used to maintain the voltage during burst. Also, the direct driver does not require the transformer component, which tends to be the second largest and second most costly component of the ultrasonic module solution, second to the transducer. In frequency support, direct drive is recommended because it is fast enough to support higher frequencies up to 1 MHz with built-in shoot-through current protection for the H-bridge driver. Transformer drivers are typically limited to 500 kHz due to the parasitic effects of most transformer components. In summary, a transformer driver should be selected when performance is the highest system priority, while a direct driver should be selected when solution size, cost, and power budget are a system priority.